of a polynomial growth on the real line and the reduction of PAPR. And the main topic is the reduction of PAPR. And this is a very important topic in the telecommunication. And these two topics are related by one function, one signal. And using the one signal, we can expand the band-limited signal of the polynomial growth and just on the real line, not whole space. And using the signal, one signal, I'm going to introduce a scheme for the reduction of PAPR. And this is very basic definition and the Changeon sampling theorem. The band-limited signal is with the bandwidth, the sigma is, if the support of the Fourier transform the real line is contained in this compact set, then this is called a band-limited signal with bandwidth sigma. And the Bernstein space is B sub sigma to the P is the set of the band-limited signals with bandwidth sigma. And the restriction of F to the real line is del to the P. Then the Changeon sampling theorem is if F is a signal band-limited to nearing pi to pi and is in L2, then this is the inverse Fourier transform. And then F can be constructed with the sampling points, the set of integers by this formula. This is the Changeon sampling theorem. And this is the Fourier transform. And then the Changeon sampling expansion holds for any signal in the Bernstein space with P is greater than or equal to 1 and less than infinite. And if the P is infinite, it does not hold. The Changeon sampling theorem does not hold. And the non-uniform sampling is if the sampling node is the Tn minus n is an integer is less than y equal to d and less than 1 core, then it forms the ridge basis in this space, L2 space. So we expand the Fourier transform with this ridge basis in this space and take the inverse Fourier transform, then we obtain the sampling theorem, non-uniform sampling theorem. So expansion in this space is important. It's important. And we want to expand the space for the sampling, and we have the growth of the signal in the Bernstein space, and the growth of the signal is f of g is less than is bounded on the real line, and in the imaginary axis it has a exponential the growth. This is the growth of the signal in Bernstein space. So if F is, the Fourier transform is in the LP and P is greater than 2, then the inverse Fourier transform should be defined in the sense of distribution. And the dual space, so we have to introduce the dual, the E prime, the distribution. So the E prime is, the E is the space of the functions which are infinitely many differentiable. E is the set and E prime is the dual space. And so the E prime, if F is in E prime, then it has a complex support, and the complex support it has a complex support. So we know that the growth of the function in E. If F is in E prime, then we have the Pell-Wiener-Schwarz theorem by this theorem, if f is the Fourier transform is in E prime, and it has a complex support, negative sigma to sigma, and f is the inverse Fourier transform, then we have the growth. The f of g is less than this. So this function is on the real line. This has the polynomial growth. So it's not bounded. So I want to expand the signal with band limited signal, and this. So the function has a polynomial growth. Yes, it's not bounded anymore. And this n is called the order of f. Order of f. So if f is in the Bernstein space, then the order of the f is the Fourier transform is 0. Fourier transform is 0. So any signal in the Bernstein space, which is not p is not infinite, then the sampling expansion, the uniform and the non-uniform sampling expansion holds. But this expansion does not hold for a signal when the p is infinite. P is infinite. So I want to introduce the sampling expansion, which has the Fourier function for a signal with bandwidth the sigma, and this signal has the polynomial growth on the real line. So we have to use the distribution theory. Since the inverse Fourier transform is defined by in the distributional sense. So we have to use the distribution theory. So the previous results, all the previous results used the distribution theory. And in here, I want to introduce one function, and I'm going to expand the function which has polynomial growth, but we do not use the distribution theory here. So Jakai introduced the class of the band limited. First, he introduced the class of band limited signal satisfying this one, and he made sampling expansion. He made a sampling expansion, and the bandwidth is sigma, and which is less than pi. Then the Jakai showed that the sampling expansion in the previous expansion holds, but the expansion does not converges absolutely. But we can expand it, and it converges the pointwise. So this space lies in the Jakai class. Since this is the Jakai class, if a signal is in here, then this is bounded, so this integral is finite. So it's in the Jakai class. And the class H sigma k is the class of all the band limited signals with the polynomial growth. And the bandwidth is sigma, and the integral of the f squared over 1 plus x squared to the k. This integral is finite, then it is called the H sigma k. So f is in E prime, and the order is n, and f has a complex support, the negative sigma to sigma. Then the inverse Fourier transform of f belongs to the k is the n plus 1. So here I want to introduce one signal, and expand a signal in the H sigma k. And this signal is important. And here in this expansion, and in the next talk by the PAPR problems. So non-uniform sampling is this one. Yes, Tm minus n is I introduced this one. And then the sampling theorem is this one. I introduced this one. And this is converges uniformly on each the horizontal strip in the complex plane. And we have the truncation error, and D is less than 1 quarter, so if n increases, then this goes to 0. So this converges uniformly on each compact set. So I want to introduce one signal, define the auxiliary signals. Yes. The phi sub sigma, phi sub alpha is the auxiliary, the band limited signal, and alpha is the non-negative integer, and satisfying the following properties. The phi sub sigma is phi sub alpha. Phi sub alpha is band limited signal, and with bandwidth 1. Yes, by scaling we can make the bandwidth. So yes, the support is there 1. And this part is important. Yes, the phi sub alpha is not 0 on the real line, and is band limited, and this has the polynomial decays. So phi sub alpha is less than or equal to some constant over 1 plus x squared, x to the alpha. So this has the polynomial decays and band limited, and is not 0 on the real line. Yes, then we want to use this node, sampling node, and using this function, the infinite product. The theorem is, the expansion is, the phi sub alpha is satisfying the previous conditions, these three conditions, and let alpha, L is the k of the alpha, and the bracket is the smallest integer, not less than this number, and delta is, so here the sigma is less than pi. Here the sigma is less than pi, and the delta is pi minus sigma. And we define for the psi, the function psi. Psi is phi sub alpha delta z over L, and to the L. Then this is the growth is this as the growth 1 over x squared, and to the L. So is the growth is 1 over x squared. In the denominator we have the power is 2 times L, and this is the band limit. The original the phi has the band limit 1, bandwidth 1, and increased by the delta of L. So then we can expand the signal in this space. When the sigma is pi less than pi, then we can expand it like this. And this x is in R on the real line, just on the real line. We can expand it like this one. The expansion is very simple. And we have the truncation error. And psi is has a growth 1 over the x to the k. It has a decay 1 over x to the k, and this psi has a bandwidth the delta, and has a polynomial decays. So we multiply by f times psi. Then the f has the bandwidth sigma, and this has a bandwidth delta. So this multiplication has bandwidth sigma plus delta, which is pi. This has bandwidth pi, and this has polynomial decay like this one. So f over 1 plus x to the k is in the L2, space L2. So this multiplication is in the Bernstein space. So we can apply the Changeon sampling theorem and the non-uniform sampling theorem. to expand this one. So we expand this one. F times psi, then we can expand this one, since this is in the Bernstein space. Yes. And now the psi has no zeros on the real line. So we can divide by this one. Divide by psi. By psi, then we have an expansion of the F, which is in H sigma k. So we have this one, but this one expansion the converges uniformly on each compact set, each compact subset. So we have this expansion. And the example of this function is, auxiliary function is 1 minus the sinc function g over pi over g square. And this is a sinc function. Then this function has a growth 1 over x squared on the real line. And this function has no zero on the real line. Yes. So this has no zero on the real line and has a bandwidth 1. So we can use this function. Then the psi is, actually the psi is, if the k is given, then psi is this function. So we can expand the function in h sigma k, and the psi is this function. Using this function, we can expand the signal in h sigma k. So we don't have to use the distribution theory in this expansion. And so using this signal, I want to introduce the reduction of the PAPR. So as the mobile form the popularized this signal is very important. Yes, when we send the data, we send the several data together, and the method is the OFDM signal. This is OFDM signal. If we have the discrete data, the a sub k, and we have n data, and we want to send this data to the mobile phone, and the method is making this the series, like the Fourier series. Yeah, this is called the OFDM signal, and we send this one. And this is the time interval is from 0 to n times t. N times t, and n is the number of subcarriers. Yes, this number as the n, and the t is the delta f is 1 over nt. And if we take, for example, the t is 1 over n, then this is delta f is 1. And f sub k is k times the delta f. And here if t is 1 over n, then delta f is 1. So this is simply, we can write this one as e to the I times 2 pi the kt. This is OFDM signal. So we send this signal to the mobile phone, and from the mobile phone we extract this data. We multiply this function and integrate. Then we can recover the a sub k. So if n is very large, then we can send lots of data together. But the problem is, then the problem happens. The problem is the PAPR. The PAPR is peak to average power ratio, and we draw the graph of this one. If n is very large, then we have high peaks. So we have the high frequencies. So PAPR is defined by the maximum of n sub nt square. Maximum, and divided by the expectation of n square, xn square. N square. So this is defined by the PAPR, and yes, the main disadvantage of the OFDM signal is if n is very large number, then the PAPR becomes very large. So we need to send the very high quantity data. But the telecommunication company have to use the certain range of the certain band of the frequencies. So we cannot send the data. So that is the big problem in the OFDM signal. So there are lots of the method reducing the reduction of the PAPR. So to reduce the PAPR, the popular method is just clipping. If we have the high frequency data, then throw it away and send it. Yes. And that method it is used now. But then we have the data distortion. So when we have recovered the data, the A sub k, then we have different data. So it makes a trouble. So the popular method is clipping and coding to reduce the PAPR. So our goal is to reduce the PAPR of the OFDM signal without any distortion of data. Yes. So the method is very simple. And taking the circular convolution between the OFDM signal and the suitable signal. And in here, having the complex support, this means for the calculation, if it has a complex support, then it has an advantage in the calculation. So it's a complex support. Yeah, so they're taking the circular the convolution between the OFDM signal and the suitable signals having complex support, then the PAPR of the convoluted signal is remarkably reduced. So first we consider the convolution method, and then derive the corresponding weighted OFDM signal. So I introduced these functions. This has an advantage since this has no zero on the real line. So phi of x is this function. It's the same function as before. This function, and then this function has the Fourier transform. Fourier transform is very simple. This one is this one. Yes. Phi of psi, the Fourier transform is this function. Has a complex property, and the near pi to pi. And this signal is an even function, and we take the circular convolution with x of n and with the Fourier transform phi. Then y sub n is this signal, and we send this signal. Instead of the x of n. This is original the OFDM signal, and this is convoluted signal. And now we take we need to recover the original data, discrete data. So we take the Fourier transform of y sub n. Then it is the Fourier transform of xn and Fourier transform of phi. Then this is just Fourier transform of xn and times phi. This is the Fourier transform of y sub n. And this is the Fourier transform in the sense of distribution. And x of n is this signal, OFDM signal, and phi has no zero on the real line. And take the Fourier transform of this one, then this is just delta function. This is the delta function. And y, the Fourier transform of yn is Fourier transform of xn times phi. So we put the 2 pi fk here. Then we have the data a sub k. And divide by this one. And phi has no zeros on the real line. So phi of yes. So the a sub k is this one. This one. But we sent the y sub n. Y sub n. So we recover from the signal y sub n. The Fourier transform of y, this is Fourier transform of xn is divided by phi. Then it is Fourier transform of yn divided by phi. And this has no zeros. So this is not zero, so we can recover the a sub k. So there is no any the data distortion in this scheme. And from this, actually the engineers does not understand this scheme. Yes, since we take the convolution, then they think that the bandwidth increase. In general, the bandwidth increase. But in this case, the bandwidth does not increase. So in this form, the engineers does not understand at all. So we need to convert this one into the other form. So that is the weighted OFDM signal. And we had the convoluted signals instead of the OFDM signal. And we can write this the convoluted signal into the weighted OFDM signal. So we transmit the weighted OFDM signal instead of the original OFDM signal. And then the PAPL is reduced almost 1/2. So phi is inverse Fourier transform of this one, and this integral is just the inverse Fourier transform at this point. So this one is phi of this one, and times this one, and xn is this one. Xn is this OFDM signal, and y sub n is this convolution. So we multiply this one and replace t by t minus cos I and the integral over near pi to pi. And this one is just y sub n is just this signal. This is a very simple calculation, and the difference of the original signal y x sub n and y sub n is, the difference is just this is a sub k, and this is a sub k times phi of 2 pi fk multiplied by this one. So we give the weight to the data. Then, so in this our system, we give the weight phi of 2 pi fk and to the data the a sub k, and we form the OFDM signal with the weighted discrete data, this data. And together, yes, and we transmit this weighted OFDM signal instead of the same time duration. Same time duration, we send this weighted OFDM signal instead of this signal. Then we can recover, like the original one, we can recover this data. We can recover this data, And after this data, since phi is not 0, we just divide this one. Divide by phi. Then we can recover the A sub k, and there is no any data distortion in this scheme. So the phi is not 0, so this discrete data is completely recovered. And we may use the function. We may use other function which is not 0 on this node. But this function is not 0 on the real line, so we can use for any n. Yes. So, and in the simulation, we used the 1000 QPSK modulated OFDM symbols. So this means data is the A sub k is 1 or 0 or negative 1. It's just the formed by negative 1, 1, and 0. That is called the QPSK, the modulated OFDM signal. And we made the experiment where the n is 2 to the 8th, 2 to the 9th, and 2 to the 10th. Yes, and with this n is this one, when we made the experiment, then this is the most important graph in the telecommunication in the PAPR. This is a CCDF graph, and this is the original CCDF graph of original OFDM signal. And this scheme, this is the graph of the CCDF graph by the weighted OFDM signal. And this is reduced by almost 1/2. This is not 0. This is 4 and 5, 6, and this is 10 and 11. And so almost 45% is reduced. And big advantage is if n is increased, then the PAPR increase in the original OFDM signal. But in this scheme, it slightly increase. So we can use the large number n, and this graph is the probability graph. Yeah. So we can reduce the OFDM, the PAPR with the weighted OFDM signal. Yeah. And yes, and it's too short. I'm sorry. Yeah. That's it. Yeah.